Hello, statistics scholars. This is our first lecture for Chapter 9, an introduction to the t-statistic, or one-sample t-test. Here are the learning objectives for Chapter 9. This is what we're going to cover, and this is what you will need to know for the next proctored exam. Think of these learning objectives as your roadmap through the chapter and your study guide for the next exam. So take a minute, hit the pause button, and read through these. In this lecture video, we will continue to explore inferential statistics. We will focus on one-sample t-statistic hypothesis testing. Specifically, we will review the z-score statistic and learn the difference between a z-statistic and a t-statistic, and learn how to conduct a hypothesis test with the t-statistic. Last chapter, we learned and practiced hypothesis testing with z-scores. We talked about using sample means as estimates for population means, and we learned how to calculate standard error to describe the expected difference between sample and population means if the null hypothesis is true. Remember that standard error, sigma m, is equal to population standard deviation, sigma, divided by the square root of sample size n. Standard error, sigma m, is also equal to the square root of population variance, sigma squared, divided by sample size n. We use the z-score statistic to help us make inferences or draw conclusions about population parameters. The z-statistic is equal to sample mean m minus population mean mu divided by standard error sigma m. The numerator measures the actual difference between sample and population mean, and the denominator measures the expected difference between sample and population mean if the null is true. Once the z-statistic is calculated, we use the standard unit normal table to find the corresponding probabilities. There are problems with using the z-statistic hypothesis test. The z-test requires more information than researchers typically have. The z-test requires knowledge of population parameters, specifically population standard deviation, sigma. Researchers usually only have sample data available, and so we need a different hypothesis test. The t-statistic or t-test is an alternative to the z-statistic or z-test. Remember that a sample statistic can be used to estimate a population parameter. The t-statistic allows researchers to use sample data to test hypotheses about an unknown population mean. The advantage of the t-statistic is that the t-statistic does not require any knowledge of the population standard deviation. For the t-test, sample standard deviation will be used to estimate the unknown population standard deviation. We will use estimated standard error SM as an estimate for standard error sigma m. So, the t-statistic can be used to test hypotheses about a completely unknown population, that is, both mu and sigma are unknown, and the only available information about the population comes from the sample. All that's required for a hypothesis test with t-statistic is a sample and a reasonable hypothesis about the population mean. The goal for the hypothesis test is to evaluate whether there is an actual difference between sample and population mean. Whenever a sample is used, we expect a natural difference or sampling error between a sample and population mean. The hypothesis test tries to decide between two alternatives. Is there a natural difference? In other words, is this due to sampling error, or is this a real difference due to something the researcher did? The critical first step for the t-statistic hypothesis test is to calculate exactly how much difference between sample mean m and population mean mu is reasonable to expect if the null is true. However, because the population standard deviation is unknown, it is impossible to calculate standard error like we did with z-tests in previous chapters. So, the t-statistic requires that we use sample data to calculate an estimated standard error. We can use sample variance S squared as an estimate for unknown population variance sigma squared, or use sample standard deviation S as an estimate for unknown population standard deviation sigma. The formula for estimated standard error is SM, or estimated standard error, is equal to sample standard deviation S divided by the square root of sample size n. Estimated standard error SM is used as an estimate for standard error sigma m when sigma m is unknown. The t-statistic formula is almost the same as the z-statistic formula. You should notice that the t-statistic formula uses the estimated standard error SM in place of standard error sigma m. The t-statistic is used to test hypotheses about a population mean mu when population standard deviation sigma is unknown. A large value for t, or a large ratio, indicates that the actual difference between the sample data and the hypothesized population is greater than would be expected if the null is true, or if there is no effect or difference. You can think of the t-statistic as an estimated z-score. The estimation comes from the fact that we are using the sample variance or sample standard deviation to estimate the unknown population variance or standard deviation. With a large sample, the estimation is really good, and the t-statistic will be very similar to a z-score. With small samples, however, the t-statistic will provide a relatively poor estimate of z. The value of degrees of freedom, df is equal to n minus 1, is used to describe how well the t-statistic represents a z-score. Also, the value of degrees of freedom, df, will determine how well the distribution of t approximates a normal distribution. For large values of degrees of freedom, df, the t distribution will be nearly normal, but with small values for df, the t distribution will be flatter and more spread out than a normal distribution. As you can see in this picture, t distributions are related to the standard normal distribution. Like the normal distribution, t distributions are bell-shaped, symmetrical, and have a mean of 0. However, t distributions have more variability, indicated by the flatter and more spread out shape. The larger the degrees of freedom are, the more closely the t distribution approximates a normal distribution. With degrees of freedom equal to infinity, the t distribution and the z distribution are the same. So when df is equal to infinity, the t is equal to the z. The t distribution is a family of distributions, one for each value of degrees of freedom. The t distribution approximates the shape of the normal distribution. Again, flatter than the normal distribution, more spread out than the normal distribution, and more variability or fatter tails in t-distribution, specifically for smaller sample sizes. In order to evaluate the t-statistic from a hypothesis test, we will need to look up a t-critical value from the t-distribution table in Appendix B or in Canvas modules. You will need to know the significance level or alpha level, degrees of freedom calculated as df equal to n minus 1, and whether the test is a one-tailed or two-tailed hypothesis test. If the absolute value of the obtained or calculated t-statistic is larger than the absolute value of the t-critical value from the table, you can reject the null hypothesis. The one-sample t-test statistic formula is t is equal to sample mean minus population mean divided by estimated standard error. If the null hypothesis is true, then the t-test statistic is equal to 0. The further away the obtained or calculated t-test statistic is from the t-distribution's mean of 0, the more likely we are to reject the null hypothesis. The hypothesis testing steps for the t-test are almost the same as they were for the z-test. 1. State the hypotheses. 2. Set the criteria for a decision and determine t-critical values using degrees of freedom. 3. Calculate t-test statistic. And 4. Make a decision regarding the null hypothesis. In the next video, we will discuss effect size and assumptions for one-sample t-statistic hypothesis testing.